Hello everyone, welcome to my channel. Today we are going to be discussing a quantile regression model with interactive effects. This model is developed by Matthew Harden and Carlos Lamache, and it uses panel data for its analysis. It also looks at dealing with cross-sectional dependence and endogeneity. We are going to use an example data in Stata to do this. So I'm going to first and foremost import my data. And you have it there. Let's browse the data and see what it entails. Alright, so the data includes variables such as carbon dioxide, inflation, ecological footprint, GDP, population growth, which come from sources such as the WDI and then the Global Footprint Network. Now the countries that we have are developing countries, and so we're looking at the effect of carbon dioxide emissions on the ecological footprint of countries, right? So our variable, that is our country variable, is a string variable, so we encode to the string, and then we set our panel. We're using XT-set2 for that, which provides a more detailed output for what the structure of the panel is. We generate variables. We need to restructure our variables in such a way that they become normal because of the skewness of variables, mostly in panel data settings. So you have we generate absolute values of these variables as population growth, GDP, and inflation rate, which have negative values within them. So mainly to be able to transform them with logarithmic transformation, we would need to use absolute values of these variables. By doing so, we then create our log transforms, and then so that we don't lose the direction of the values, we apply the signs to them by using the relative value of the variable itself, or the raw variable, and then its absolute, so we don't mess out on the signs. Let's summarize our data and then produce a pairwise correlation for that. So you see missing values within our data for some of the countries, and we see that our negative values for these three variables, that is GDP, population growth, and inflation rate. Again, you find that carbon dioxide has a high correlation with ecological footprint, which is consistent with the literature. So we look at cross-sectional dependence. We test for that using Pisarran's model, and we find that the variables are cross-sectionally dependent, and so there's cross-sectional dependence in our model or in our data. There's also heterogeneity, as by doing this you can find that the delta values are less than 0.05, so there's heterogeneity in our data, and which is very obvious with pattern data. Now, in trying to solve for this and allow for cross-sectional dependence, we want to partial out or take out the cross-sectional dependence in our data. We need to so that it doesn't bias our results, we need to create cross-sectional averages, and that is how this model by Carlos Lamache and Harden deals with it. So we provide we provide the averages of common factors, right? So in this case, averages for independent and dependent variables, and so we do that. And then optionally we could also include lags of averages. I've already done that too. And then our interaction. So and this should be backed by theory. I mean, when you're dealing with the interactions, you need to look at what the theory says about them. But I mean, since this is an example data, we just it still may align with theory. So you find that we generate an interaction between ecological footprint and carbon dioxide emissions, population growth, carbon dioxide emissions, and what have you. So we do that, and then you could also as well expand the averages to include the interactions. I mean, averages of interactions, but we do not do that here, as Carlos and Amash do not also hint on doing that. So let's take that out. Let's go straight to our model. And so we use the command IVQ regress for that. Our instrument is the first lag of carbon dioxide emissions. Then our quantile range is from the 10th quantile to the 90th quantile. So as you can see, you have our independent variables, our interaction effects here, and then the averages of the independent and independent variables. Right, so after this, after looking at how the results are, we just plot to find out what the trend of the endogenous variable effect on the dependent variable looks like. As you can see from the results, you realize that there seems to be some heterogeneity in the results, especially looking at the endogenous variable carbon dioxide. You see that at lower quantiles it is positive, which is in line with a vast number of the literature. But as we continue down the lane, it becomes negative. I mean, as we move on to higher quantiles, you see a stronger negative value. And the 90th quantile, which is countries with high ecological footprint, they have a negative effect. I mean, carbon dioxide emissions have a negative effect on ecological footprint, which could be explained. I mean, given that countries with high ecological footprint may also have been investing hugely on renewable energies, and that may offset that effect of carbon dioxide emissions. And so they may not necessarily be increasing their footprints, but then although carbon dioxide emissions may increase, so a 1% increase in carbon dioxide emissions for higher quantile countries will lead to a minus 1.27% decline in ecological footprint, and that's how you explain that. So let's plot this. Right, so you see it's trend downwards from the lower quantile up there to the higher quantile. Right, let's continue. We try to use this post-estimation test to derive whether our variable, our endogenous variable, is indeed endogenous, and whether the effects that we find in the graph is also strong, and what have you. So let's do that and see what it gives us. Right. So from the first effect we try to test, so I said the null hypothesis is no effect. But when you compare the statistic and the critical value, you find that there's indeed some effect. The second null hypothesis says constant effects, but it says that the effects varies because of the high statistic compared to the critical value. Dominance says that the null hypothesis is that it's strictly negative or positive. But in this case, since the statistic is higher than the critical value, it means that it's not strictly positive, or negative. It fluctuates, so it's either positive or negative at a certain point, and we find that in the data. the results that we had. And then exogeneity, that's the null hypothesis here, which says that our endogenous variable is exogenous rather, but from the statistic here you find that it's greater than the critical value, which means that our endogenous variable is indeed endogenous, so we are right on track. Let's deal with the cross-sectional dependence. Let's test for whether there's still cross-sectional dependence in our model. The GOS here for a static model, as you may well know, says that it's 1, which means that there's likelihood that there's cross-sectional dependence. Let's wait for our XTCD2 results for residuals. Yes, there's still cross-sectional dependence. So there's strong cross-sectional dependence. So yeah, this could mean that there's still some common factors that need to be that still are within our data, which needs to be included here. So certain variables that we have included, which may better explain this dependence, are supposed to be included in our model, which we haven't. And since it's an example data, there's left for you to also explore, with other data that you find. But pretty much this is how you go about it. Very simple, but it requires a lot. So thank you very much for joining and for following this particular discussion here. I hope that you would hit the subscribe button, hit the like button as well, then share widely so that others know about this and are able to apply this very intuitive model. Thank you very much.